I'll go from current slide. And before we get started there, let me hit a couple of announcements I think I've told you before several times about the North Scholarship at Alabama A&M. They've got that going, so you got the email, check it out, see if it's anything you're interested in. Okay, there was a meet the artists, talk with the artists. That's going on right now on the Birmingham East Campus in Thelma Catlin, so it's too late. I just got the announcement printed this morning, so they didn't give us a lot of time on that. But you can go anyway because it's now. Okay, now this is just future stuff. This coming Friday, I have a dermatology appointment at 9:15. So I haven't figured out whether I'm going to the Birmingham campus and work for 45 minutes and then go to the appointment and then go back to the Birmingham campus. I will if there's any need for me to do that. It just seems like it'd make a lot more sense if I spent those 30 minutes driving and 30 minutes driving, the hour doing something better like grading or something like that, rather than driving back and forth. So I've got to check with my boss and see what he thinks on that. I will try to go to the campus after the appointment's over with, but I don't know how long the appointment's going to be. I'm hoping 9:15 to 10:15 will be the max that it would be, but you never can tell with doctor's appointments, ever. So if I did get through at 10:15, then it would probably be 10:45 at the earliest that I'd be able to get there. And if they let me go earlier, I might get there earlier, or if they're later, I'd be later. So I don't know for sure, but I'll be there at least till 12, unless something really wacko happens and I can't get away in time. So that's this coming Friday. The next Friday, I have meetings down in Mobile, Alabama. I'll have to leave around 6 in the morning. How long does it take to get to Mobile? About 6 hours?
Well, it's about 4.5 or 5 hours.
Really?
Yes, sir, I think so.
Okay, good. Okay. Then I won't have to leave quite as early. The meeting is from 12 to 3. I've got to drive to Mobile, attend the meeting, and drive back. I don't have to do that, but I think I'm going to. I'd prefer to do that than spend the night.
Yes, sir. The directions to Alabama. It says 3 hours and 36 minutes.
3:30?
Yes, sir.
Going the speed limit?
I would imagine it says 265 miles.
265.
So if you divide that by 60.
Yeah, 265 divided by 3. Divided by 4 would be 60 miles an hour. No, more than 60. And divided by 3 would be 80 miles an hour, more than 80. I have that feeling that's going a little fast, but shoot, I should be able to do it in 4.
Yes, sir.
Or, yeah, 5. So I might not leave until my normal leave time, which would probably try to leave around 7, because the odds are, yeah, if I can eat breakfast at home, drive there. I think they'll have luncheon because they said something about menu things. So eat lunch there and then drive home and probably catch supper on the way home. So I think I would stop on the way home. That's just too long a drive, having driven that far. So thank you for that. Someone else had told me it was a lot longer than that, but I hadn't checked it myself. Okay, so anyway, that's the next Friday. This Friday, dermatology appointment. Next Friday, in Mobile the entire time. And the following Friday, I have a eye appointment. Okay, when you get old, things just are falling apart. But the interesting thing is, the guy is not at Eye Foundation Hospital, which I thought he would be. He'll be across the road here at UAB West. So that will be very convenient being here. The trouble is, usually on Fridays, I'm on the Birmingham campus. But I think what I will do is come over after the eye appointment, because the eye appointment is at 8:15 in the morning. So I think I'll come here and park, walk across to find the appointment, and then once I'm there, and I know they're going to dilate the eyes and everything else, if when I get back I feel like I can drive safely, my eyes aren't giving me too much problems, with all the stuff, then I'll drive on to Birmingham. If not, I'll work here. But how much I can work without being able to see well, I don't know. But I'll determine that then. And that's getting us awfully close to spring break. So I'll be here spring break Friday before spring break, but that's about all. Okay. So those are the upcoming things that I know about right now. So my Fridays have been shot for a bit. All right. Any questions on anything we've covered so far? Okay. Then we're left off at I think the top of page 714, area of the surface of revolution. Is that what you have? Okay. And that's where we're starting today. And it says you can use the formula for area of the surface of revolution in a rectangular form to develop the one for a surface area in parametric form. Now, if you recall, your arc length formula was, it's going to take me a while to get back. Well, there it was there, I think. That one. Okay, parametric form for an arc length. Now, forget the 4 there. Okay, that was because we had those 4 lobes. That's why the 4 is out there, and whatever the limits are. But that's the basic equation or formula for an arc length. Okay, now take that and imagine that you're taking this arc and revolving it around, say, an axis. Okay, then that's going to be that arc length formula times the circumference of the axis, right? And the circumference is 2 pi r. So it depends on what the r is. If okay, so it says you can use formula for area of a surface revolution in rectangular form to develop a formula for the surface area in parametric form. Rather than going back there, use what we just did, the arc length, okay, like I just said. So the area of a surface of an arc length of revolution, if a smooth curve, capital C, is given by x equal f of t, y is equal g of t, does not cross itself on an interval a to b, okay? Then the area S of the surface of revolution formed by revolving C about either one of the coordinate axes. So they're going to make it easy for you here. They're going to do across the, if y is equal g of t, then this would be around the, around the x-axis, because y is the value here, and you revolve that, 2 pi times g would be the radius around the x-axis, and f would be the radius around the y-axis. So you just introduce that, and there you would have it. Now, let me get, I forgot to mark you here. You aren't here yet. I'll soon get you here. Hold on. All right, you're here now. Okay. I forgot to mark. Clark's here. I forgot even to put the dates in. Today is the 25th, just 10 shopping months till Christmas. Okay. 26, 27, 28. Fill up this week, and Brian's here. So the bottom part of the alphabet doing quite well, whereas the top part we don't know.
What's happened to Vince?
I don't know. He's been in and out some, and I hope you won't mind saying he had a weird thing come up with his roommate. They either chose to move or had to move or something like that, but they had talked about it, planned it, and everything else. And then when the day, and arranged it and everything, the day for the move came, the guy couldn't come up with the money for the thing, so Vince had to pay it. out of his Pell money that he was going to use for the course or something. No, I think he's being reimbursed by his company. So he had to use money he was going to pay for the course, part of that to pay for this, so he had a partial payment. And he was really, I think, having to work hard, extra hard to try to get back. So I don't know. He may have had to withdraw. I don't know. Haven't heard. So I hope he didn't mind my saying that. But he was just livid at this guy because he needs them to pay the rent, but the guy didn't pull through. So I don't know. Yeah.
I've had roommates before, so.
Yeah, right.
Never again.
Now, if it's not the x-axis or the y-axis, if it's something parallel to the x-axis or y-axis, okay. Now, of course, they say here it does not cross itself. Also, really probably shouldn't cross the x or y-axis either, or the axis of revolution. So if this was the y-axis, but you're moving over here and your curve's over here, then it would be this, you just extend this minus that would be your radius of revolution. If it's over here, so you add or subtract from whatever y, and y is equal something, or x equals something, and then use the appropriate formula. A lot of arm waving there, but hopefully that made sense. Okay. Those formulas are easy to remember if you think of the differential of the arc length as, and that's exactly what I said. If you don't go back to the other, but do the arc length formula, which was this, well, just make an integral here and you got it. And then this would be 2 pi GOT in front of that if you're going around the x-axis, and 2 pi f of t if you're going around the y-axis. It's exactly what I said, only I didn't use the ds's. I used that thing right there, which to me is the arc length formula. Goodness, I got something in my eye. I don't know what it was. Okay, let's see. Okay, this is example 5, which is the next one here. Let C be the arc of a circle, x squared plus y squared equal 9, from 3 to 0. From the point 3, 0, I thought that was an interval there. That's what I don't like about interval notation. From 3, 0 to 3 halves, 3 root 3 over 2. Okay. All right. Pretty obvious 3 zeros on this one. Okay. Square 3, you got 9 plus 0 is 9. Yeah, that's on that curve. That's good. This one has a little more figuring to do here. 3 halves squared is 9 fourths plus 3 squared is 9. Root 3 squared is 3. 3 times 9 is 27 fourths. So 9 fourths plus 27 fourths. 9 and 27 are 36 fourths, and that sure enough is 9. Okay, so that's on the curve also. Okay, so from this point to that point, let C be the arc of that circle, shown in this figure. Find the area of the surface formed by revolving C about the x-axis. Okay. Now, certainly it doesn't cross itself. That's a nice, smooth curve with no doubling back on itself or anything. Now, here's, boy, looks like maybe that's that cataract replacement I might have to have in my eye, okay? What it looks kind of like to me, or a contact. Okay. That's a little bit better. Okay, a contact lens maybe. And find the area of the surface formed by revolving C about the x-axis. Now, if you're trying to do this with just that formula, it's kind of doable if you were to do you want to do your dx's, and the point is it's so much easier to do it parametrically. That's the whole reason for doing this. So what would this parametric equations be? Well, this is r, which is 3 times the sine theta, 3 times cosine theta plus 3 times sine theta is equal to 9. That's for certain, sure. And your theta is going from 0 to, what point is that? Okay? On that curve, what would be your theta that you would be dealing with there? There's a real kind of part of me that wants to say it's pi thirds. Let's see if pi thirds work. Yeah, because you take out the 3's, that'd be 1/2 root 3 over 2. So I think that's the pi thirds, right? So I think that's the easy way to do the problem. Okay? So let's write in parametric form.
So, how did you get that cosine?
Wait just a second, let me get my pen back. Oh, I knew that. Okay, that's how. Okay. From physics and everywhere else in vectors, your y is always the sine of this angle. If this is the angle and this is the radius r, then the y coordinate is r times the sine of theta, because the sine theta is the opposite side over the hypotenuse, which is your r, and the cosine is the adjacent side over the hypotenuse r. Make sense? So then x is equal to r cosine theta and y is equal to r sine theta. Okay. I just use it all the time in vectors so much I forget that people haven't been dealing with those. They might not see that's where it is. And then the good news coming out of it is if you had r being 3, right? Okay. And x being r cosine theta, this would be r squared cosine squared theta, right? Plus r squared sine squared theta equal 9. Well, if r is 3, so that would be 9. This would be a 9. Factor out a 9, and you have sine squared theta. I'm rearranging slightly, plus cosine squared theta. And what in the world is that? Yes, 9 times 1 is 9. So yeah, that makes perfect sense that way too. But that doesn't tell you how you got it. It just shows that works in this equation. But that is how you got it. Okay. Now, so if we have those as our parametric equations, let me write them down. I thought I got rid of that. There we go. Okay. So x equal 3 cosine theta and y equal 3 sine theta. And then this arc here is represented going from 0 to pi thirds. You got the pi thirds, right? Okay. All right.
But another question I have here is, how do we have a radius of 3? I mean,
Okay. Okay. That goes back to when we did those conic sections. Remember, we went through those fairly quickly. X squared plus y squared equal r squared is always a circle. Always a circle. Another way to write it would be x squared over r squared plus y squared over r squared is equal to 1. That's always a circle. Now, if your denominators were different, x squared over a squared plus y squared over b squared equal 1, that would be an ellipse. You either stretch them out one axis or the other. And if you had a difference in there, x squared over a squared minus y squared over b squared, or reverse those, is equal to 1, then you have a hyperbola. Yeah. So remember, but if those are equal, and over r squared, those are the same, that is a circle. So, and they told you, let C be the arc of the circle. So they told you it was a circle, and the circle is always x squared plus y squared equal r squared. Or x minus h squared plus y minus k squared equal r squared. In that case, the hk would be the place from the, this is a circle at the origin. If you had h was 3 and y was 7, then it would be up there, you know, or k was 7. It would be, the center would be elsewhere. But without a displacement x, you know, a translation on vertical or horizontal is at the origin. Yes. All right, so that would be our parametric, those would be our parametric equations then. Okay? And that does give you this, and we've just shown why that's true. So now your surface of revolution, I'll call it A, area of surface of revolution, would be 2 pi, because you got 2 pi r, okay? Oh, and you're taking this and revolving it around the x-axis, so we're going to use the y value here as the radius. So I'm going to write it in this form, 2 pi times the integral. Now I'm going to put r in here. This r is not the 3. Well, no, it's not the 3, okay? That's not what I'm meaning by r here. Times the square root of dx d theta squared plus dy d theta squared d theta. Okay? Using those parametric equations. Now what this r here is the radius about you're revolving. So this is the y value. What is the y value? This one. So that's what goes in. That's the function that goes in here. So, oh, and the limits will be from 0 to pi thirds. 60 degrees, by the way. So that area of revolution will be 2 pi, from 2 pi r being the circumference that twist around. And you're doing the limits from 0 to pi thirds of, and your r here is your y value, which is 3 sine theta. So let's bring that out and make it a 6. Sine theta times the square root of, but we got to do our derivatives first. What is dx d theta? Okay, minus 3 sine theta. Perfect. And what is dy d theta? 3 times the cosine of theta. Perfect. Okay? So if you put those in and square them, you have the square root of the dx is, and when you square and minus, it becomes plus. That'll be 9 times the sine squared theta plus 9 times the cosine squared theta. How convenient. And then you have a d theta. Okay. Now, I think you can see pretty clearly that the 9s can come out, but the square root of 9 is 3, so this jumps up to 18. 3 times 6 is now 18. So that will be 18 pi times the integral of sine theta. I shouldn't have done, yeah, that's okay. I've already pulled the 3 out. And what's the square root of Sine squared plus cosine squared. One. Okay, so that's just 1 d theta. That's not too bad of an integral to take. Okay, so this is going to be 18 pi. What's the antiderivative of sine theta?
Negative cosine.
Negative cosine theta. I can't write for some reason. Cosine theta evaluated from 0 to pi thirds. All right, so that would be 18 pi times, and what is the cosine of pi thirds? Second? Cosine. 1/2, yes, okay? Because remember, it's the x value, and this x value, take out the 3, because that's just the radius, that would be 1/2. So the cosine is 1/2. So you have a 1/2 here, minus, oh wait, it's a minus 1/2, isn't it? Because it's a minus cosine. Yeah, cosine of pi thirds is 1/2, but you negate that. And then you negate the negative and make it the positive to do the lower limit. What's cosine of 1? I mean, cosine of 0. 1. Okay, I gave it away, sorry. So that would be a plus 1, and minus 1/2 plus 1 would be a plus 1/2, and 1/2 of 18 is 9. We keep fiddling with that, so this is 9 pi. Now, I didn't do this on purpose too badly anyway, but you see, if I erase that part, it says the surface of revolution has a surface area of 9 pi. So they gave you the answer there on the figure, but I didn't want you to look at that yet. Okay, no, I just drew that. Accidentally covering the answer. You believe that? I've got some swampland in Florida, I'll show you. Okay, all right. For a really good price, too. Okay, so you see how they got that? All right, that's how I did it. Let's see if they did it any differently. Any questions before we leave this? Okay? Yay or nay? Okay. So let's see how they did it. You can represent C parametrically by these equations, x equals 3 cosine t, y is equal to 3 sine t, as long as t is going from 0 to pi thirds. Note that you can determine the interval for t by observing when t is equal to 0, that t is equal to 0 when x equals 3, and t is equal to pi thirds when x equals pi 3 halves. Oh, okay, yeah, that's with the radius multiplied in. Okay. All right. On that interval, C is smooth, Y is non-negative, and you can apply theorem 10.9 to obtain the surface area, and that will be 2 pi times the radius now being the x value, the y value, I'm sorry, 3 sine t, times the square root of the derivative of this one is negative 3 sine squared t. Sine, they put up there, that's fine. And the derivative of that is 3 cosine t squared. And this will give you 9 sine squared. That will give you 9 cosine squared. And factor out the 9. Take the square root of that, and it becomes a 3. And by the way, they pulled this 3 out and made it a 6, just like we did. They're going to pull another 3 out. Not yet. Out of there. And the rest of it was a 1, so you have 3 sine t, evaluated from 0 to pi thirds. And that's going to give you minus 18t. If you pull that out, then the minus, antiderivative of sine was minus cosine, so they pulled the minus sign out here too. And then they evaluated cosine from pi halves to 0 to pi thirds. Now I left it in there and evaluated negative cosine. It's okay to do it this way too, okay? And that would be 1/2 minus 1, but negative 18 pi out here. And negative 1/2, or 1/2 minus 1 would be a negative 1/2, and that changes that to a positive 9 pi. So almost the same way we did it. Yeah. Minor little changes. Same answer though. That's the good news. Okay, that's the end of section 10.3. And my goodness, I hadn't noticed this. This book does not have those checks at the end, checkpoints or whatever they call them, that the pre-calculus algebra and trig books that are written by the same author. They just don't have those. Every now and then they'll have larsoncalculus.com. But anyway, so homework exercises here would be 5 or 7 or both. They're both at Calc Chat, 5's at Calc View. Any of the odds 9 through 17, they're all at Calc Chat, 13's at Calc View. Either 19 or 21, they're both at Calc Chat, 19's at Calc View. Either 23 or 25, they're both at Calc Chat. Either 27 or 29, they're both at Calc Chat, but 29's at Calc View. Do 31, that's the only one like that. Any of the odds 33 to 41, that goes on to the next page too, they're all at Calc Chat, 33's at Calc View. Any of the odds 43 to 47, they're all at Calc Chat, 43's at Calc View. Any of the odds 49 to 53, they're all at Calc Chat, 51's at Calc View. Do either 55 or 57, they're both at Calc Chat. And then I would say either 59 or 61, they're both at Calc Chat. And then any of the odds 63 to 67, they're all at Calc Chat, 65's at Calc View. And then either 69 or 71, they're both at Calc Chat. There's an Exploring Concepts 73 and or 75 if you wish to try those. They should be at Calc Chat if they do those. I don't know if they do or not. There is a 77 I think probably would be good for you to do. It's a Calc Chat. 79 would be good. It's a Calc Chat. I would say either 81 or any of the odds 81 to 85. 85's on the next page. They're all at Calc Chat. Do 87, it's a Calc Chat. 89's a Calc Chat. And then any of the odds 91 through 95. And they should all be at Calc Chat. Okay. That's all we're going to do in Chapter 10. And basically, if you think about it, we talked about 10.1, but just went through it quickly. But then we only actually did 10.2 and 10.3. So those two will be on your next test along with what we do in Chapter 11. Because polar coordinates and polar graphs, if you need those, I'm pretty sure you can follow up. We were just given the formulas for those, so that's okay. Area and arc length in polar coordinates, it's nothing too new. It's just getting used to using polar coordinates. That's 10.5. 10.6 is polar equations of conics and Kepler's laws. Well, if you ever need that, you'll do it in a Kepler's laws in a physics or astronomy class or something, so I don't see any reason to go over it here. We just don't have time. And then that's it for Chapter 10. Now we move to 11. So you're only responsible for 10.2 and 10.3. So let me get out of this, and we'll go to Chapter 11. And we'll do 11.1. Now, in this chapter, I think we're going to have to do not every section, but I think 11.1 through 11.6. Okay? I'll try to do them quickly. I'm not doing very much at all quickly these days, so we'll have to just do as we can. All right. We'll start with vectors in the plane, and hopefully this is old hat to you. But if it isn't, it's not that hard to grasp, I don't think. All right. 3 objectives here. Write the components form of a vector. Pretty straightforward. Now, neither one of you have had physics, or have you? You have. Okay, but you have. Okay. So this is really old hat to you, right? Okay. Perform vector operations and interpret results geometrically. We'll do that fairly quickly, hopefully, too. We'll write a vector as a linear combination of standard unit vectors that is really almost number 1 again in some senses. Okay? So let's first talk about the component form of a vector. This almost is doing it backwards from how I learned it, but it's okay. Many quantities in geometry and physics, such as area, volume, temperature, mass, time, can be characterized as a single real number, scaled to approximate units. Area, square feet, square meters, square inches, square yards, square centimeters, whatever, okay? Volume, cubic feet, cubic yards, cubic, same deal. They're just numbers. Temperature, 98.6, you have whatever units you have, Kelvin, degrees Celsius, degrees centigrade. They're just numbers. Mass, how much of an object there is, okay? That's just a number. Time, just a number. Characterized by a single real number, scaled to appropriate units of measure, okay? Now, those are called scalar quantities. That's why they threw in the number, or scaled to appropriate units. I would never have thought of putting that there, except they're going to talk about scalar next, okay? And the real number associated with each is called the scalar, okay? Just a number. It could have units, but it doesn't have direction. That's the key. Just a quantity. Other quantities, such as, let's start with displacement, as opposed to, they didn't mention here, they could have distance. Distance is a scalar quantity. Displacement, though, is a vector quantity. The distance from home to here, let's just say round it to 20 miles, okay? The displacement from home to here was 20 miles to the southwest, okay? That has a direction. Because when I drive home, if I go the same route, I'll drive the same distance, but I'm not driving in the same direction. My displacement will be from here to home, which will be 20 miles to the northeast. So distance, scalar, displacement has a magnitude and a direction associated with it. Velocity. Velocity is the time rate of change of displacement. So that carries with it the concept of a direction. 20 miles per hour in this direction, 40 miles per hour, it has a direction associated. Now, speed, scalar. Velocity, vector, speed, scalar. They start with the right letters, right? So, just like displacement and distance, they start with the same letters, but distance is a scalar, displacement is a vector. Velocity, speed, velocity is a vector, speed is a scalar. Acceleration just about always is a vector, because you're accelerating in some direction, okay? So there's not we'll say the magnitude of the acceleration, but we don't have a separate word for that. And then, good old Newton's second law says that force is equal to mass, which is a scalar quantity, which is just going to scale it, times acceleration, so force is a vector quantity. You don't apply force to something without implying the direction of that force. Always forces have directions because they have the potential to accelerate. Okay, so these all involve both magnitudes, just like these did, but now also directions. They cannot be characterized completely by a single real number. You have to have some sort of direction element to characterize it completely. Okay? So what we use is these things called a directed line segment. Okay? Which means you start at some point, cleverly called the initial point, and you go to some other point that you're going to stop, so let's call that the terminal point. Then the vector, which connects those 2 points, gives the direction of motion, and the magnitude gives the magnitude of motion, okay? So that's a directed line segment. Now, when we refer to that in this notation, we always list the first being the initial. Even if it was pointing in this direction and P was here and Q was there, we still call it PQ. P being the initial point, Q being the terminal point. Vector PQ. That means starting initial point P, terminal point Q. Okay? And to indicate it's a vector, then they put the little vector symbol in it. Okay? Now, that directed line segment PQ has initial point P, terminal point Q, and a length, magnitude, denoted by, and here's this symbol for that. It's like double absolute value bars, which is sort of convenient too, because absolute value is always what sign? Positive. Well, your magnitude of a vector, no matter which way that vector is pointing, the magnitude is how long it is. So again, the distance, the length, which is always positive. Okay? So in that sense, this is a bad representation of that, but that means the magnitude or the length of it. Notice we still have the vector symbol here, but the magnitude loses that. Taking the magnitude of it or its length, you don't worry about its direction anymore. Directed line segments that have the same length and directions are called equivalent, and later we'll call them equal. Okay? Because if they have the same magnitude and same length, they're equal vectors. Even though they may be starting and ending from different positions, if they have same magnitude and same direction, they're equivalent, and later we'll call them equal. So if all these lengths are the same, and obviously all the directions are the same, even if you had one up here, or down here, or wherever, as long as the direction was the same and the length was the same, they're equivalent or equal vectors. That means we can take this vector here and move it anywhere on the plane that we want to move it, or once we get three-dimensional, in space that we want, as long as don't change the length and don't change the direction. You're fine. Okay. Equivalent vectors are directed line segments. They haven't named it vector yet. The set of all directed line segments that are equivalent in a given directed line segment PQ is called a vector in the plane. So we're saying the vector is a thing that's equivalent to every one of those. Same magnitude, same length. That's going to be the vector. Sort of a weird way. Now, in the book and on the slides, they will write the vector as a bold letter. Or they'll write it as PQ in regular print with a vector symbol over it. Since I can't write bold, I will put a vector symbol over the V to indicate that's supposed to be bold. It's a vector, okay, not a scalar. V without being bold or without the symbol would mean that we use that to represent the magnitude of it, okay? In typeset materials, vectors are usually denoted by lowercase, bold-faced letters such as U, V, W. So they could have others. When written by hand, however, vectors are often, that's what I was just saying, written as U, V, W. Now, most of the time when I'm writing, I don't get both wings of the arrow there. I usually make it look more like that. So mine won't be quite as pretty as that, and that'll be a shock to you, I'm sure. Okay. It's not that funny. Okay. Be sure that you understand that a vector represents a set of directed line segments, each having the same length and direction. It's a weird way to do it, but it allows you then to say they're not equal. That is the vector representing all of them. Okay. In practice, however, it's common not to distinguish between the vector and one of its representations. We'll just say that's the vector, okay? Where it could be the set of all vectors, okay? And there is a reason for that, and we're going to get to it in a minute. All right, example 1. Let V be represented by directed line segments from, now this is a point, 0, 0, to another point, 3, 2. Let U represent the directed line segment. Oh, I'm sorry. V was the directed line segment between those two. U is the directed line segment from 1, 2 to 4, 4. It says, show that U and V are equivalent. Well, right now, what do we have under our belt to determine whether they're equivalent or not? Have to have same magnitude and the same direction. Okay. Now, without having gone into it specifically, they're calling on you to recall from your past what the length of a line between 2 points is. And you remember that distance formula? That's what they called it. Square root of the change in x squared plus the change in y squared. Now that's probably not how you think of it, but that's really what it was, right? Okay. Now what's that difference in x? Oh, this is, let me put it like that so you realize. So between this first 2 points, d would be, now, if one of them is bigger than the other, I like to use bigger minus smaller. It doesn't matter because you're going to be squaring it. So it's 3 minus 0, which is 3 squared, plus 2 minus 0, which is 2 squared, and this would be the square root of 9 plus 4, which is the square root of 13. There's the length or magnitude of v. Okay? Magnitude of the vector v is that. Let's do the same thing for u. You want to do that in a different color or what? Just do it in the same color? Okay. Let's call this dv, distance of v. This will be the distance of u, du, okay? Not dv, okay, never mind. Square root of, let's do this one. 4 minus 1 would be 3 squared, plus 4 minus 2 would be 2 squared. Guess what? That's the same thing. So these two distances, this is distance of v. I probably should put my arrows over them too. And the other is the distance or the length of u. So this is the magnitude of u. Okay, see, mine only have one thing. So we've got the magnitude being the same. That still doesn't guarantee they're the same vectors. Because what else has to be true?
If we go in the same direction.
Yes, the directions must be the same. Now, what is one way we define a direction? This is a really vague question. But in a plane, how do we determine the direction it's going? Or maybe a derivative, how do we determine the direction it's going?
Positive or negative.
Okay, there's certainly that.
Or what degree?
Okay, yeah, what degree it is, or the angle it makes with some reference angles. Let's say the horizontal. Remember, that's how we usually do it. Horizontal, positive horizontal axis, and we would use this angle in between here. But what functions usually operate on angles? Math 113.
It's several years ago for me now.
Huh?
It's several years ago for me now.
What was that covering? 112 was pre-calculus algebra. What was 113? Trigonometry. So what trig function would be the best to talk about direction it was going? Tangent, exactly, because it's change over x, change of y. In fact, it was rise over run, right? Y over x. That will give you its direction. Well, let's do the same thing here. And we've already done it. The delta x here was 3. The delta y here was 2. Delta x here was 3. Delta y here was 2. The tangent of both of those vectors would have been, I use the term, 2 over 3. 2 over 3. So yes, the magnitudes are the same and the directions are the same. So I think that's all we have to do. Let's see what weasel words the book uses to describe this. Okay? If P00 and Q32 are the initial terminal points of V, and just like they gave here, 1, 2, and 4, 4 are the initial and terminal points of U, then there are the two vectors drawn. Now, I didn't draw them, but we basically talked about them to death. Okay, and what we can do then are measure use the distance formula to show that they have the same length, and sure enough, that PQ, magnitude of PQ, would be 3 minus 0 squared plus 2 minus 0 squared, which is square root of 13. And for RS, it's 4 minus 1 squared plus 4 minus 2 squared, and that would be the square root of 13. Both line segments have the same direction because they're both directed toward the upper right on lines having the same slope. Now, they didn't say how you got that slope. Here we go. Slope of PQ is 3 rise over run, 2 minus 0 over 3 minus 0, 2/3. Slope of RS would be rise over run, which would be 4 minus 2 over 1 minus 4 minus 1. And again, that's 2/3. Makes sense. Good deal. Because PQ and RS have the same length and the same direction, you can conclude the two vectors are equivalent. That is, U and V are equivalent, or later we will actually call them equal vectors. Okay. The directed line segment whose initial point is the origin is often the most convenient representative of a set of equivalent directed line segments, such as these two that they show here. This is the one that's usually the best. And we'll see a really classic, you might say, reason why that's the best. Okay?
Will there always be a relationship between two sets of points,
Be a what?
I guess there will always have to be, you could subtract the, 0, 0 from 3, 2.
Right.
Or the 1, 2 from 4, 4, and you get 3, 2.
Yeah.
Will it always be that way?
Yeah, for their magnitudes and directions to be equal, they have to. In fact, the magnitude, certainly the change of x and change of y have to be if they are the same, then the squares are the same. You add them together, that's going to be the same. So certainly for the magnitudes to be the same, that's got to be the case, that the differences have to be the same. For direction, if those differences are the same on both of those, then obviously the ratio of the differences are the same. The only reason you can't say that would imply the other is that you could have one of these being twice as long, and then the ratios are still the same, so the direction's the same, but the magnitudes aren't. Okay, you could have the magnitudes the same, but not the ratios of the directions the same. So one doesn't imply the other, but if you have them both, you know they've got to be. Yeah. So if those two are the same difference, yeah, you're at least halfway there to proving they're the same vector. This representation of V is said to be in standard position. This one here, nu V. Okay. Now here's the key. Here is what they're been sort of angling toward. A directed line segment whose initial point is the origin can be uniquely represented by coordinates of its terminal, that is V1, V2. Okay? Now, back here on that one, see that point initially is at the origin and then going to V2. and demos here. Okay, good deal. Okay. Now, oops, went too fast. All right. So similarly here, P is 0, 0, and Q is out there at some V1 being the X component, V2 being the Y component, whatever they happen to be. Okay? Now, V1, V2 in parentheses is the terminal point, with the initial point being 0, 0. The vector V, represented by vector PQ, could then be represented by its coordinates. I'm sorry. These are coordinates of a point. These are components of a vector. And when the initial point's at the origin, the coordinates of the terminal point are exactly the same as the components of the vector. Now, if you had this other vector up there like we did before that was parallel to it, then you have to have the difference. Let's call it U1, U2, U3, U4. And U3 minus U1 would be the same as V1, and U4 minus U2 would be the same as V2. If that's the case, then it would be, and those were the same values, then it would be represented by the same vector V1, V2.
And so the standard position is coming from...
Say that again.
The standard position is coming from 0, 0?
Yeah, and that's what we mean, yeah. This representative V is said to be in standard position. A direct line segment whose initial point is the origin can be uniquely represented. So that's the standard position, and you're measuring everything from the positive x-axis. Though they're not saying that here, but ultimately we'll get to that. Okay. In this definition, note the difference in notation between the component form of the vector, angle bracket V1, V2, and the point V1, V2. That should be parentheses there. They should not be brackets. If it's not, there's something severely wrong with my problem, with my thinking here.
That's how it is in the book.
What? This way?
No, sir.
Yeah, I know. I'm trying to find it. Yeah, there it is. Right, top of page 753. Yeah, this should be parentheses, parentheses. Not a point is always designated by ordered pair or ordered triplet or order whatever in parentheses. A vector is always angle bracket, not parentheses, not curved, angled. All right, and that gets us ready for this definition. If V is a vector in the plane whose initial point is the origin, standard position, and whose terminal point is some point V1, V2, then the component form of that vector V is angle bracket V1, V2. The coordinates V1 and V2 are called the components of V. If both the initial point and the terminal point lie at the origin, then V is the zero vector, and then denoted by bold 0, which I would have to write 0 with an arrow over it, and that would be components 0, 0. Now, there are two things wrong with the zero vector, in my mind. What does a vector have to have?
Magnitude and direction.
Okay, what's the magnitude of the zero vector?
0.
0. That's not much of a magnitude. Now, tell me the direction of a zero vector. It could be pointing anywhere because it's not pointing anywhere. I mean, there's no initial and terminal point. They're the same point, so there is no direction. Absolutely no direction and a zero magnitude. It sort of lends itself to failing being even a definition of a vector, except that you have to have it for what we call a vector space. You have to have a zero component there. So we have to have the zero vector. That definition implies that any two vectors, U1, U2, and V1, V2, are equal if and only if U1 is equal to V1 and U2 is equal to V2. I told you we're going to get around to not calling them equivalent anymore, but calling them equal, because if the two components are identically the same, then obviously the vectors are identically the same. It can't be U1, U2, and U2, U1. They are the same, but in reverse order. They have to be the same in the same order. And if that's true, they are equal. That's going both ways, if and only if. All right. Now, the procedures listed below can be used to convert directed line segments into component form and vice versa. So let's imagine we have PQ, P being the point P1, P2, Q being the point Q1, Q2, are the initial and terminal points of the directed line segment as we initially stated. And notice here they're not saying P is necessarily the origin. If it's not, then you can't assume anything until you get this down. Then the component form of the vector V represented by PQ is Q1 minus P1, this is angle bracket, Q1 minus P1, comma, Q2 minus P2, another angle bracket. That now is the vector V. V1, V2 are those components. Remember, this is always initial, it's always terminal. Your differences are always terminal minus initial. Terminal minus initial. Back when we did distance, didn't matter because you're going to square them. With a vector, it does matter. Okay. Moreover, from the distance formula, which you see here, the length of the magnitude of V, here it doesn't matter which order you put them in. You still do difference in x's and difference in y's. And that gives you V squared plus U, because this is V1, this is V2, so it's V1 squared plus V2 squared. And that's going to hold for all vectors of all magnitudes. I mean, of all, what is the term for it? Dimensions. A three-dimensional vector, seven-dimensional vector, whatever those are. It's the square root of V1 squared plus V2 squared plus V3 squared, or all the way up. And those being the differences of those two endpoints. That's the magnitude of a vector V. Okay. Make sense? And notice here, it doesn't matter what order you put them in there because you're going to square them anyway. All right. But it will matter on your direction. So if vector V is V1, V2, right now, until otherwise told, in fact, the title of this section is Vectors in the Plane. If you're in the plane, that's two-dimensional. If you're in space, that's three-dimensional. Okay? So right now, this section is all in the plane. Two-dimensional vector. V1, V2. X, Y. Okay. Then V can be represented by directed line segment in standard position from P, 0, 0 to Q, V1, V2. This is saying the same thing we did earlier in reverse. If that's your vector, earlier we said if you represent the vector in standard form, then these coordinates become those components. Now we're saying if these are the components, and then you put your vector from origin, your Q is going to be at that point, V1, V2. The length of V is called the norm of V. All right, when we get it down, okay. We call it the length of V. We call it the magnitude of V. Now we're calling it the norm of V. All those mean the same thing. Okay?
Reminds me of Cheers.
What's that?
Reminds me of Cheers. The show Cheers.
Huh? Oh, yeah. Okay. Okay, got it. Norm! Yeah, okay. I remember that. Okay. The norm of V. Okay? And if the norm of V is 1, then magnitude of V is 1, the length of V is 1, then we call it a, what's another term for 1? Ever play that card game that you call out something when you only have one card left? Uno. It's the unit vector. Unit vector. Okay, no, the unit vector. V is any vector who has a magnitude of 1 is called a unit vector. Moreover, if the magnitude of V is 0, that's if and only if V is the 0 vector. You can't come up with a 0 from our definition to be anything other than 0, 0, which to me is not much of a vector. But you have to have it. All right. Now, they're skipping example 2 before they move into vector operations. So let's pick up example 2. This may be where we have to do it. Find the component form and the length. So we want component form and length, okay, of the vector V. That's sort of got on my line there. With initial point, I'm just going to call it P. Is that okay? That's what they've been calling it. 3 minus 7. And terminal point Q, negative 2, 5. Oops. Negative 2, 5. Almost started making my comma the 5. All right, we'll write it all again. Okay. We want component form and length or magnitude or norm of V with those initial and terminal points. Which you want to do first? Component form or magnitude? I really don't care too much. What's the component form?
Is that the changing Y?
Okay, say again. Okay. You're starting with the Y's? Is that what both of you are doing? It's okay. Yeah, I'm just asking. Okay. Huh? No, I'm just asking. Both of you started with Y. You said 5 and negative 7. Is that what you said?
Negative 5, 7.
Oh, you're doing it all at once. Okay, yeah, got it. The first one is negative 5. That comes from negative 2 minus a 3, because it's always terminal minus initial, comma, and what you say the second one was?
7.
Nope. You said 7?
Yeah.
This is a negative 7 here.
Oh, I thought it was a 2.
Oh, making fun of my writing. Okay, I got it. I'm not too hurt. Okay. What would that be?
12.
12. Perfect. Okay. That is the component form of that vector. Okay? Now, what's the length of that vector? Once you have this, and what's the symbology for the length?
D.
Huh?
D. D. Letter D.
Okay, you could do that, but using just the letters we have, not introducing any new ones.
Oh, Q.
Okay, we do the double bars. That's magnitude or length or norm, the double bars of V. And what would that be? Same definition that you're thinking of for D. What would that be?
The square root
Of?
negative 5 squared plus 12 squared.
Right, and that would be the square root of?
25 plus 124.
144. Is that what you said, right? And what's the square root of, what is 25 plus 144?
169.
Okay. And what is the square root of 169?
It would be, what, 17?
13.
Oh, 13.
The other 9. Okay. if you got a calculator, pull it out and see, but that is square root of 169 is 13. Now, they all are not going to come out whole numbers. Don't even guess that they would. They just did this one so it would. Okay? Magnitude, a scalar number, of course, the vector is a vector number. Has to have components in it. Okay. And this implies magnitude and direction. There's the magnitude. Direction would be given by the arctangent of y over x. Okay. I sort of threw that in a little early, but it's okay, I hope. Okay. That is example 2. Now, let's turn to vector operations. Vector operations. Here's the definition of vector addition and scalar multiplication. And by the way, these two, the combination of these two quantities or operations or whatever you want to call them define what it is to be a linear function of some nature. So you'll see these always show up together. Something another addition and scalar multiplication. So here's vector addition. Let u be this vector given in component notation by u1, u2. V be this other vector given by its component notation v1, v2. These are two vectors, and C is any old scalar number. Okay. The vector sum of u and v is then u plus v, and what you do with this is you take the first component of u, add it to the first component of v, that gives you the first component of your sum vector. So the sum of two vector is the vector comprised of their sums of their corresponding elements. And then for the second component here, take the second component of u, add it to the second component of v, and that gives you the second component of the sum vector, u plus v. Okay? So hopefully this would be just like you would expect. Okay? Now, here's a scalar multiple rule. C being that scalar over there, and u being one of the two vectors, u perfectly fine. If you were to do c times u, that scalar times this vector u, what that means is basically you distribute the c over both elements of the u. Now that's not quite the right use of distribute, but to me it makes sense. So it would be cu1, comma cu2, which means this. Remember we call this a scaling factor. So if you went from a short vector here to a longer vector here, notice we didn't change the direction of any, just changed its length. You scaled the length upward here. But if you went from this vector here to this vector here, you scaled it down. But same length. Well, guess what? If you went from this one to this one, you had to increase the x and increase the y. So, yeah, the c is multiplied by each of the components. If you went from this one, people at home can't see what this one is, to this one, then you're scaling both of those, your x and your y, down. Okay. So, it's cu1, comma cu2 in vector component 1. Now, that was what the definitions are. Then throwing an extra one in here for no extra charge. The negative of vector v, say this one, is negative v. That would be like c was negative 1, so it would be negative 1 times u. Well, that's negative 1 times v, right? So that would be negative 1 times v1, comma, negative 1 times v2, which is negative v1, negative v2. You just negated everything, which is the same as multiplying by minus 1. Now, what that really did was take this vector here and make it that vector there, you know. You changed its direction exactly 180. Same initial point, you just flip the terminal point to the other side. You've negated it. Everything, both components. Okay. Now, if you remember how we subtracted signed numbers. What did we do? We kept the first number the same and then added the opposite of the other number. So if it was a 7 minus 3, you know how to do that. That would be 4, but it's 7 plus a negative 3, which is 4. But 7 minus a minus 7, we just changed the sign and added. So it changed 7 plus a positive 7, which is 14. Same thing here. If you're taking the difference of these vectors, u minus v, is the first vector, never change that, no reason to change it, plus the negative of the second vector, which would then be u1 minus v1, u2 minus v2, which is exactly what you would think, u1 minus v1, comma, u2 minus v2. Yes, exactly what you would guess. And if these were signed numbers, you follow all the rules for signed numbers, which are exactly these same rules. So now we threw in there, vector subtraction is just the opposite of vector addition. Okay? It is a form of vector addition. You're just adding the opposite of the second vector. Now, geometrically, the scalar multiple, this is saying the same thing I was arm waving on the board, of a vector v is a scalar c, and a scalar c is the vector that is the magnitude of c times as long as v. Okay? So if this is v, and you have half of v, then it would be exactly half the length. Now notice it didn't have to start from here. It could have been down here, anywhere here. And twice v would be twice the magnitude of v. Okay? And that could have been starting and ending from any one of them. And minus v would be exactly the opposite direction of v. Now you just reverse your initial and terminal points. And minus 3 halves v, they quite do the same thing here. That would be negating, but also expanding by 1.5 times. Does that make sense? If c is positive, then cv has the same direction as v, but if c is negative, then c has exactly the opposite direction. Not just somewhere down there, exactly the opposite direction. Okay? Now, the sum of two vectors can be represented geometrically by positioning the vectors without changing their magnitude or direction. Remember, that's why we can move them around anywhere as long as we don't change that. So that the initial point of one coincides with the terminal point of the other. Okay? So if this is vector u, and that's vector v. If we're going to add v to u, we leave u where it is and take v and just translate it up here. Don't change the magnitude or the direction, and that will give you the resultant vector will be from the terminal initial point of u to the terminal point of v. Once you put the initial point of v at the terminal point of u, then you've just added the two vectors. Okay? Now, something you might note, if you had taken vector v first and then moved u over to it, you'd wind up at the same point, which is another way of saying u plus v is the same as v plus u. It doesn't matter. We'll get to that later, but it doesn't matter the order. In other words, vector addition is commutative. Doesn't matter which order you do it. And that's what we're saying here. You starting with v, adding u to it, you wind up with the same u plus v that you did there. It's just located at a different position. Whereas if you, whatever. Okay. So you move the initial point of v to the terminal point of u, or move the initial point of u to the terminal point of v, you're going to wind up with the same vector. U plus v and v plus u are exactly the same. Doesn't matter how you write it. All right. What we call those u plus v or v plus u are the resultant vector, the result of vector addition. And by the way, doing them in this order, then in this order, makes a parallelogram here. So what you have here is what they sort of call the main diagonal of that parallelogram. Not this one here, but this one here. Okay? So we sometimes call this vector addition, when you draw it out like this, the parallelogram method of vector addition. Okay? Which, to me, it's just graphical addition. But that's why they call it parallelogram method. Having UV as adjacent sides. Figure 811, which was, 11.8, I'm backwards today, shows the equivalence of the geometric and algebraic definitions of vector addition, scalar multiplication, and presents at the far right a geometric interpretation of U minus V. Well, without saying anything else, let's just do it, okay? So here we've just seen, if you take vector U and V and move them both to the origin, as standard position, so they both have their initial point at origin, then you can either start with either one, U, and then translate the V up here and get U plus V this way, or you can do V right where it sits and then take U and translate it here. You get the same result. And this shows kind of geometrically exactly what you're doing. Let's say down here we're doing V plus U. So you start off with the magnitude of V, okay? I'm sorry. V1, which is the horizontal component of V. I'm using different, there's V1, which is this value here, V1. Well, here's your U1. They didn't show it over here, but U1 is this distance here. We'll take this U1 and move it over here, add it to V1, and you get to here. Here is V2. It's pretty short here because that's the magnitude of V in the vertical direction. Here's the magnitude of U in the vertical direction. Take this and put it on top of that, and you're right up here. Now, if you did the same thing down below, started with U1, which was here, but start with it here, and you can be down here. It doesn't matter where you do it, just keep it horizontal. And then add V1 to it. Well, here's V1, add that here, and you're going to get to the same U1 plus V1, okay? Or, and then after you've done that, start with U1 here, U2 here, that's the Y component of U. U2 here, and add to it the V2 here, and you get to the same point there. So all the way around, that's vector addition. All right, let's do scalar multiplication. All right, here is U1. Here, rather than C, they're using K. If K is a number greater than 1, and they don't show anything really about K, but if you start with U1 here, magnitude of U in the horizontal direction, U1, and then multiply it by K, you get this. U2's here, multiply it by K, you get that. And then your KU vector will be KU in this direction that's been scaled upward from U1 to KU1. And that same amount of scaling here from U2 to KU2, then that's what you got. And you see you're always on the same line. Okay. Now this K was a little bit more than 1. No, let's see. A little bit more than 2. Because, at least in my mind, that isn't quite, it's a little short, a little more than twice U. All right, then the vector subtraction. I never think about subtraction this way, not completely anyway. Here's what I do. Part of it is exactly what I think of. If you have U minus V, that's the same as U plus a negative V. Well, here's the U right here. Keep it right there. Then add to that negative V. Well, this is V. That will be negative V. So you add this magnitude, but going in the opposite direction there, this is going to be U plus a negative V, which is the same as U minus V. Now, they draw the u minus v out here. It would be just as well here. This could be u minus v plus or minus v. I don't try to read too much into this. This is, they are showing something, that u minus v is going to wind up being the directed line segment between v and u, going from the terminal of u to the terminal of v to the terminal of u. I never try to remember that because I'm going to screw it up. So what I do, if I am doing the drawing, I put u plus a negative v and then draw it over there. I never mess with that because I'm afraid I'm going to forget which way it goes or whatever. Get me in another quadrant and I get all confused. Okay. But if that's something you want to remember, yep, that works too. All right. Because basically what you've got there says u minus v is u plus a negative v. And that's what your answer is, that's u minus v. Then what you're doing is this added to that should give you u, and sure enough, v plus the difference here gives you u back. How you check subtraction is by adding, right? And that just shows you that works. If that's helpful. If not, do whatever you want to with it. All right, is this a first test coming in?
Yes.
Good deal.
Last time I forgot to.
Huh?
I was saying I meant to give it to you Wednesday. I forgot to.
Oh, okay. Yeah. All right, and remember, there are research papers that can be done too. And let me say this too. We're getting really close to midterm. We got this week and Tuesday of next week, and we're right at midterm. I think Wednesday of next week is the middle of the term, or midnight between Tuesday night and Wednesday morning. That's midterm right there. Now, as soon as midterm gets here, they're going to ask me, all the instructors, by the way, for midterm progress reports. And midterm progress reports, for me to give, what they want to know are students who have a D or an F at midterm. Okay? Now, if I have zilch turned in by midterm, guess what? That's a grade of 0, which is going to go in as an F. Not that it means anything, but it might just mean someone's going to start calling you or bugging you or something. Do you need tutoring? Do you need some counseling? Do you need... So to avoid that, get me something in. I think most of you have turned in something. Yeah, most of you have. Okay. All right. So let's do example 3. Here's V, negative 2, 5, and W at 3, 4. Find each of the vectors. Okay. Can anyone tell me what 1/2 of V would be? Negative 1 will be the first component. 5/2 is the second. Or 2.5, or however you want to say it. 5/2 to me is just as good as any. How about W minus V? Can anyone tell me what that one would be? I didn't need to make it that big. While y'all are figuring, let me reduce it somewhat. It looks fairly outrageous. That's not a 7, that's an angle bracket. Okay. I knew someone would be griping. I'm killing time trying to get someone to give me an answer. 5. What you said? Negative 1. Perfect. Start with the first one. 3 minus a minus 2 is 3 plus 2 is 5. 4 minus 5 is a negative 1. Okay? Now this one might take a little more work. And if you need to, take as many steps as necessary. But if you can do it in your head, we can do that too.
first one is 8.
A little louder.
8 for the first one.
Okay, the first component.
Yeah.
Okay. It's V1, which would be -2, right? Plus 2 times W1.
Oh, yeah.
Oh, yeah. Okay.
It's 4.
4. Okay, got it. First component 4. Does everybody see how he arrived at that? No. Okay. Well, take as many steps as you need. You can write it out and write it what 2W is. That would be 6, 8. And then you add 2 to 6, you get 4. Right. Or you can do it this way. I think the way he was doing it, that's how I did it. V, first component of V, -2, plus twice the first component of this, 6. -2 plus 6 is 4. Okay? Second component being 13. Got it. 5 plus twice 2, twice 4. 2 times 4 is 8. 5 plus 8 is 13. Good deal. Now, don't let me rush you through this. Take as many steps as it takes for you to see and understand what you're doing with it. Okay? Now, I think I'm going to need to erase this to see, but y'all got these answers? Okay, let's see what they did. 1/2 of V would be 1/2 of -2, comma 1/2 of 5. That would be -1, 5/2. Perfect. Okay? V would be W minus V, which would be the angle, the vector W, 3, 4. Well, they're doing it this way. 3 minus a minus 2, which is 5, comma 4 minus a 5, which is -1. Got it. 5, -1. And then the next one. 2W, oh, they're doing it this way. 2W is 6, 8. I said you could do it this way. And V plus 2W would be -2, 5. That's V plus twice W would be that. And when you add those together, you get 4, 13. Whoops. -2 plus 6, comma 5 plus 8, -4, 13. All right, any questions? Okay, are we almost out of time? Oh, we may be a little past time. Huh? 209? Okay, I guess, well, yeah, it'll take a while to talk through these, so we'll start next time with, and by the way, there were a couple of people featured in your text here, the first being William Rowan Hamilton, and he was done some of the earliest work in vectors. He was Irish, and they consider him probably the premier mathematician from Ireland, whereas the physicist would have been James Clerk Maxwell. Okay, but then on the next page was Emmy Noether. Interesting person here. My understanding, when Einstein had problems with math, he went to Emmy Noether. Okay, she was that good. She was also, I know Einstein was at least part Jewish, he may have been totally. She was either part Jewish or totally Jewish, and because she was Jewish and a woman, she got out of Germany before Nazi took over. Same as Einstein. Thank goodness they came to the U.S. And the sad part was she went in for, I think, a routine appendectomy, and something went wrong on the operating table. She died on the operating table. It's just one of the most routine operations around, and she died. Who knows what she could have done, but she's a pretty incredible woman. We'll start there next time. There went my minute, right?
Exercises or?
Oh, yeah, I forgot to say the exercises. Not too many. Number 3, that's at calctrack.com. 5 and 7, both at CalcChat. 5's at CalcView. 9 through 15, they're all at CalcChat. 11's at CalcView. Going backwards on it, do 17. Magnitude of vector 19 to 23, 17's at CalcChat. 19 to 23, they're all at Calc Chat. 21's at Calc View. 25's at Calc Chat. I think you can do, yeah, you can do 27. It's the Calc Chat and Calc View. And you can do any of the I's 29 to 33. They're all at Calc Chat. We'll hold off there and pick up next time. Okay. Thanks for reminding me.